We solve this equation. We solve this specifically Woodward-Fisher rules, which conjugated and dynes and trines and polys according to the rule where the specifically towards the parent values homoannular dyne, then parent values for the heteroannular dyne as like this. For example, the lambda max for the component here. Already we take a consideration of the first example in this case, that is, yes, here is the 1,4-dimethyl cyclohexane 1,3-diene is the CH3. Here is what solution contains compound and homoannular dyne. Means here cyclic dyne contain double alternative double bond having alkyl substitution in both of sides. So what will have parent two alkyl substitutions here there. So 2 into 5 it will give 10 nanometer and 2 rings residues are there. So 5 into 2 it becomes 10 and the parent value for homoannular dyne is 253 nanometers. So total become 273 nanometer. It is a calculated value, but observation on the instrument it will give 265 nanometer. So this is the way of theoretically we calculate the values for the conjugated dyne, trines and polymers and observe with the values of the instrument acquired from the instrument. So another example, lambda max of this compound, which is heteroannular dyne. So parent value is 215 for heteroannular dyne. So and 4 ring residues are there. Here is a 1, 2, 1, 2. So it becomes 4. So 4 into 5 becomes 20 nanometers. So calculation becomes sum of is 235 theoretically and observed value by practically is 236 nanometer. Then another example is compound having the structure as like this. So according to there is a heteroannular dyne ring is residue is there. So we add value 215 nanometer. Then ring residues are there. Here 1, here's 2, 3. Ring residues is the residues which considered from this double bond. Here is double bond, not with here. So there is a 3, 1, 2, 3 ring residue. So it will become 3 into 5, 15 and exocyclic. Here is exocyclic E indicate exocyclic bond of this cyclic of B cycle. So it becomes 5. So total becomes 315. So same values are obtained from both calculated theoretically and observed in practically in this way. So then Woodward-Fisher rule for the alpha beta unsaturated compound. So alpha beta unsaturated compound having the same parent value increments for the different substitutions are there. So alpha beta unsaturated acyclic or 6-membered ring ketone having the 215 nanometer. Then alpha beta unsaturated 5-membered ring ketone having 202 nanometer and alpha beta unsaturated aldehyde having 207 nanometer as the parent value. And increment values are for the alpha position, beta and gamma position respectively 10, 12 and 18. And each exocyclic double bond have 5 nanometer value. Then double bond conjugation is 30 nanometer and homoannular conjugate and dyne 39 nanometer. So another increment values are containing oxochromes are OH, OR, SR, chlorine, bromine and so on. Methoxy group containing compound. Alpha beta position according to 35, 30 and 50 respectively for OH and so on. So these values are used for the calculating theoretically according to Woodward-Fisher rule as the lambda max for alpha beta unsaturated carbonyl compound. So example of this carbonyl this compound containing specific groups. So alpha beta unsaturated acyclic ketones are there. So alpha beta unsaturated cyclic ketone having a value 250 nanometer, alkyl substitution alpha position 10 nanometer and it will give calculated value 225 nanometer and observed value is 220 nanometer. So according to here is another example having different types of the extension and parent value. So it is alpha beta unsaturated 6-membered ring, cyclic ketone is there and alpha position having the ring residue. Here is the 4 ring residues are so becomes for 2 ring residues and double bond exocyclic ring 2 rings and calculation. So According to that, we put up the values and we will get the calculated value 295, sorry, 59, and observed value is 256, as like this. So these are the examples that will give the idea about how we can calculate the Woodward lambda max according to Woodward-Fisher rule for the alpha beta unsaturated carbonyl compound. Then important last point from this chapter or in of UV spectrophotometry is the application. So qualitative and quantitative analysis is main important thing is related with this application of UV spectrophotometry, is that it used for the characterizing the aromatic compound and conjugated olefin, and it can be used to find out the molar concentration of the solute under the study. So qualitative and quantitative both type of analysis done by this UV spectrophotometer. Lots of the methods are available, calibration curve method and absorption method, then simultaneous equation method, multi-component equation method, and all those things. So according to that we can find out whatever we want to analyze or we want to calculate specifically value. So the determination of impurity is also done by this. So it is one of the important method to detect the impurities in an organic solvent, detection of isomers and possible. So determination of molecular weight also done by the BS Lambert. So we apply the values to that equation and we get the values with respect to weight also. So there is important thing is simultaneous equation method. So this method is also we follow in our day-to-day practical of the UV spectrophotometry. So we'll also get idea in detail in our practical also. So it is the theoretical part related to this simultaneous equation method. If the sample contain two absorbing drugs, is X, Y, Z for example, so each absorb at a lambda max by 2 other than that is the lambda 1 and lambda 2. So it may be possible to determine both drugs by the lambda simultaneous equation method. So it will be graphs shown in this way by the UV spectrophotometer X and Y. Here is X and Y, peak lambda max of both of the compound at different nanometer. After that, the information required is very important in this case is absorptivities. So we calculate the absorptivity according to the specifically formulas, and for X and Y at lambda 1 lambda 2 in both of cases of absorptivities X and Y, and we will get X1 and Y1, and we put up all these values in our equation we made by the as a simultaneous equation. And this absorbance of dilute sample is Y1 and Y2 for A1 and A2. According to that we will get CY concentration CX and CY for X and Y respectively sample, and the absorbance of mixed in the sum of individual for X absorbance X and Y. So we put up all those values for equation 2, 1 and 2, and multiple equation we'll get for 3 and 4. According to that we will get the multiple equation in this case, and after we putting a value we'll get these equations are known as simultaneous equation. So simultaneously we'll get this equation of 1 to 5, 1 to 4 or 1 to 6 according to that, and solving the simultaneous equation each point will determine the concentration afterward X and Y in this sample. Then another absorbance method is also available. In that absorbance ratio is modified on a simultaneous equation procedure, and this quantitative assay of this component administered by the absorbance ratio method, and absorbance are measured at a wavelength of lambda max one of the components. So it is absorbance method lambda 2 and other being wavelength equal absorptivity of the two component Y1, that is isoabsorptive value. So these are isoabsorptive values are from this collected in this graph, and we accordingly put up the values in equation, and after solving all these equations we will get the concentration by the absorbance. So these are the references which have I preferred for to prepare this presentation. So thank you very much for listening this important phenomena principle theory related with our first chapter from the unit first, that is UV spectrophotometry. Thank you very much.